Reward seminar. This is the benefits of 650V GaN FETs for 800V power converters section being presented by NATARAJAN. My name is Fei Yang, and I will be the moderator for the session. All participants are muted for the session. Please use the chat function to ask a question and address it to everyone. We will be answering the questions throughout the webinar in chat. Also chat if you're having any problems hearing or seeing the presentation. With that, I will hand it off to Ramana to get started.
Thank you, Faye. Hello, everyone, and thank you very much for your interest in wanting to hear about why 650V GaN FETs can offer a compelling performance advantage in power converters where the DC link voltage is much higher than the rated voltage capability of the devices. So here's the agenda for today. First, we'll put things in context and take a look at what are those applications which are driving towards very high DC link voltages and what are the trends involved within those applications. Next, we'll take a deep dive into the various power switch options available for these high voltage power converters. We'll particularly look at how these different switches perform in terms of switching power losses. And then we'll go on to make the case for why 650V GaN switches can offer a compelling advantage. In the third section of the presentation, we'll spend some time to review some clever power topologies and architectures which can really enable the use of these devices in power converters where the bus voltage is higher than the voltage rating of these devices. In this context, we look at stacked series half-bridge arrangements as well as multi-level power converters. And finally, we'll close with some conclusions. In recent years, many applications have emerged which process multiple kilowatts of power through them. And in order to be efficient, they have leveraged the use of very high DC link voltages. Examples of these applications include AC-DC battery chargers for commercial energy storage facilities, DC-AC grid tie inverters, which send the energy back to the grid from either a battery bank or a photovoltaic inverter, high power test and measurement equipment that we are commonly used to seeing in the labs, such as AC sources, and finally, emerging electric vehicles, which are fitted with bidirectional AC to DC and DC to AC onboard chargers, which process multiple kilowatts of power. Typically, in all of these applications, the energy is supplied from a utility three-phase AC line, where the line-to-line voltage is as high as 400 volts AC. Once this power enters the power converter and it is corrected for the harmonics using the input power factor correction stage, what results is a very high DC bus voltage, typically anywhere between 600 and 1000 volts. So this is one prime reason where you see power converters where the DC link voltage is as high as shown here. Another reason is emergence of high voltage batteries, which offer a higher energy density, such as in electric vehicles, where the emergence of 800-volt batteries offers the opportunity to charge these vehicles faster and also offer a longer driving range. This is yet another reason where we run into power converter applications where the DC link voltage is about 800 volts or higher. In all of these applications, what's quite important is high efficiency and high power density. So it's common knowledge that higher operating frequency is a pathway to achieve high power density. Okay? And this is being requested for various different reasons in these different applications. But fundamental to all of them is the desire to shrink the passives, the energy storage components, the inductors, the transformers, the EMI filters, and the storage capacitors. Now let's look at some reasons why engineers desire to shrink the passives. Firstly, something as straightforward as the component cost. Something smaller should cost cheaper, and so there's a desire to reduce the size of these components to reduce the component cost. In some applications, which are operating in harsh environments, there is a need to reduce the weight of the power converter and also have a slimmer power converter, which means you have reduced the height of these components, because in the end, this results in better shock and vibration performance. In some applications, the total volume is extremely restricted in all three dimensions. This also calls for the need for a smaller XY footprint on the PCB. A classic example here on the right-hand side is the electric vehicle onboard chargers, where we clearly see the need for higher and higher powers being processed through the chargers in order to charge the vehicle faster. So we see the trend for the power to increase from 6 to 7 kilowatts today to about 11 to 22 kilowatts in the future. And all of this needs to happen with little to no increase in size. So this really means the application is pushing to almost double the power density of 4 kilowatts per liter in the coming years. Getting back to the reasons why there's a desire to shrink passives, in some applications which desire very high efficiency, such as data center power supplies, there is simply a need to have smaller magnetic components to create cleaner and smoother airflow pathways, which offer an opportunity for better cooling and a lower temperature of operation of the semiconductors, which result in higher efficiency. In some applications, such as DC-AC inverters, operation at the highest switching frequency really enables better wave shaping and lower distortion for the AC output voltage, which is fed back into the grid. And finally, almost common to all of the applications is a desire to go to automated assembly and manufacturing, which is greatly enabled by the use of surface mount technology components, and that is where the need for smaller components makes a lot of sense. But fundamental to all of this, before something can be made to operate a high switching frequency, it first has to become more efficient. Before you can make things smaller, you have to make them more efficient because there is less space available now to extract the heat. So fundamental to all of this is the power converter must have overall lower switching power losses. And once you're able to achieve that, now you have created a pathway to actually crank up the system operating frequency and take advantage of all of these benefits. Okay, so the goal of this presentation is really to answer the question, is there any benefit related to using 650 volt devices, even if the DC link voltage of the application is much higher than the 650 volts? Conventional wisdom says the most straightforward way to implement power converters is to choose devices where the voltage capability of the device is higher than the DC link voltage. Looking at the left-hand side, we have the traditional half-bridge two-level power converter, where each switch for, say, an 800-volt DC link application would be rated over 1200 volts. And when the switches are off, they would need to support the entire DC bus voltage. This is a traditional way of thinking. But here then is there the opportunity to differentiate by really looking at some alternative architectures which cleverly enable the use of lower voltage rated switches in these applications. A couple of examples are shown here, such as the stacked series half bridge on the left-hand side. And over on the right-hand side, we have a three-level power converter with flying capacitors. And we look at these in more detail in the coming slides. But our goal here to answer the question, what benefit is there to use these 650 volt devices in these very high DC link applications? It all comes back to the switching performance of these devices. So let's take a look and compare how the switching performance of these 650 volt devices compare to the traditional 1200 volt devices. But before we do that, let's go back and refresh our basics here for a second. Any power switch, as we all know, is very non-ideal. It has these parasitic capacitances between the gate and the drain to source, as well as capacitances between the drain and the source, what we call the output capacitance. And every time the switch turns on and off, these capacitances have to be charged and discharged. And there is a time duration when this has to happen. And the longer the time duration extends, more is the time when a high voltage and high current overlaps, which causes higher switching power losses. Not only that, in some power switches, such as power MOSFETs, there is the inbuilt body diode shown in the dotted line here. And the stored charge and the reverse recovery charge of this body diode further contributes to energy losses in every switching cycle. So the goal here to understand what are the various attributes of the power switch which influence the different components of the switching power loss. Let's consider the case of a hard switching application. And looking at the waveforms during turn on, first we have the interval where the drain current of a switch that is off has to now rise up to the load current level, which you see here. Once the drain current has reached the load current level, then the drain voltage starts slowing down. And when this happens, the additional current is needed for discharging the output capacitance of these FETs and also the reverse recovery of the associated body diode. So in this phase where the drain current is slowing to the load current and the drain voltage is dropping from the DC link voltage to the turn on voltage, you have an overlap of high current and or high voltage. And this is what we call the switching overlap loss. And now if you look at the turn off, something similar happens where you have the drain current increasing and drain current decreasing and the drain voltage increasing. And this is again an instance where there is high switching overlap losses. Now, if you go back and try to associate this with what attribute of the power switch is influencing the time duration for these overlap losses, it fundamentally comes back to the point that these parasitic capacitances and charges, they need to be managed and discharged or charged during the turn on and turn off instance. And that fundamentally comes back to the ability of having a strong gate driver and also having low gate source and gate drain capacitances for these devices. As far as the time duration when the output capacitance is charged and the reverse recovery is discharged, that is directly associated with the device's output capacitance and how it varies over voltage, and also the capability of the body diode inside these switches. Next, when you go look at the soft switching application, here the smart architecture enables a zero voltage turn on, which is a situation where the drain current, the drain voltage first has to slow down to the point where the reverse conduction starts happening. When the reverse conduction starts happening, then now the current is growing through the body diode or through the third quadrant of the device, following which then the device is actually turned on by its gate, and then you have the zero voltage turn on. So here there are very little overlap losses and these components go away. And what really remains is basically the overlap losses which only occurs during the turn off. And again, the power losses in the soft switching application then comes back to how you're able to manage the time duration when there is an overlap of the high current and high voltage at the same time. Now, let's look at these different power switch options available and study how the hard switching and soft switching power losses compare. First off, let's define a figure of merit. We can use simple test setups such as a double pulse tester to measure the switching energy during turn on and turn off. And then we can normalize that when you're comparing different power devices by multiplying the switching energy loss with the on resistance of the device. And there's a need to do this in order to fairly and reasonably compare devices with different on resistances. And it is also important to account for the on resistance at high temperature because the behavior of the different power switches is different with regards to its temperature coefficient. It is well known that, for example, some devices such as gallium nitride have a higher temperature coefficient and they'll have a higher RDS on compared to others in the market, such as silicon carbide devices. So to have a fair comparison, we can normalize the switching energy for the FET which is measured using double pulse tester by multiplying with the on resistance at high temperature and define what is called a figure of merit. Then we can go on to plot this figure of merit as a variation to the load current which is processed during the double pulse tester. This way, we can now get an understanding of how the switching energy of the device behaves and varies as a part of the load current. And here again, there's the opportunity to differentiate between what happens in a hard switching application and what happens in a soft switching application. In a hard switching application, we have all the turn on and turn off losses and also the output capacitance and reverse recovery losses. And then for soft switching application, we have primarily the turn off losses only. So plotting the hard switching figure of merit over load current and comparing the different devices. And herein, we have compared a 650 volt GaN FET, a 650 volt silicon carbide FET, and a 900 volt silicon carbide FET. you could clearly see that the GaN device has the lowest switching energy figure of merit compared to the other two. Furthermore, it is very linear and increases with the lowest slope, whereas we start to see some quadratic behaviors with some of the other technologies available in the market. Another observation worth noting is the higher the voltage rating of the device within the same technology, the power losses further tend to increase. The switching energy loss further tends to increase. And that is understandable because higher voltage switches typically also have higher capacitances associated with them, and they switch slower as a result of that. A similar trend is also seen in the soft switching application, where the GaN devices have very low switching energy loss as a function of the load current compared to the other technologies in the market. So this really makes the case that if you have a desire to push the switching frequency of a converter, there is a significant benefit to be had if you're able to use a lower voltage rated switch in the power converter while cleverly managing the switching voltage that the FET has to sustain based on the DC link voltage of the converter. So GaN devices, 650 volt devices, offer certainly a compelling advantage for high frequency operation. Now, we have talked about the technology. Now, how do we engineer a product which is actually optimized for high frequency operation with the lowest switching losses? One smart way to do this is to integrate a gate driver along with the GaN FET in a very low inductance package. And this enables very low gate loop inductances and enables the gate driver to offer the highest peak currents for the fastest switching of the GaN device. This greatly contributes to minimizing the IV overlap losses using turn on and turn off. Furthermore, having these products arranged in a very low inductance package, such as a QFN package, with very low common source inductance and gate loop inductance compared to other through-hole packages in the market, enables the switch to have ability to switch high DIDTs and achieve high peak currents during the switching transients. This helps to in turn reduce the overlap time when the DVDT and the DIDT happens between the drain to source. And making the part available in a topside cooled configuration enables the use of liquid cooling arrangements, which are far superior and also becoming increasingly common in some of these multi-kilowatt applications. And this gives the capability to achieve very low thermal resistance between the junction of the device and the cooling plane, less than 2 degrees centigrade per watt, which can easily allow for about 30 watts of power dissipation in the package if one were to assume that the coolant is at 65 C and the maximum junction temperature to operate is about 125 C. And when all of this is put together and furthermore added with integrated protections localized within the device, you have now a product which is really engineered for high frequency operation, high power operation with robust capabilities to withstand the harsh switching conditions in these applications. Now, let's get to the second part of our presentation, where we'll start looking at a few different power topologies and study the benefits of one topology over the other. The traditional half-bridge topology, which is a two-level switching converter, which you can see here in the switching waveforms, where there are two levels of voltages sustained across the transformer. These offer certainly the lowest device cost and the fewest number of switches. These are very well understood and have been used reliably for many years. The disadvantage, of course, is now you have to use a higher voltage rated devices, which we have seen higher losses associated with them. They also have to sustain the full bus voltage, which results in increased voltage stress and again, higher switching losses. And from the passives perspective, these passives now see the highest volt second on the inductor, which then results in large level of magnetics. And of course, the large level of magnetics is also needed to achieve low voltage distortion. Looking at alternatives available, there is the enhancement of this two-level into the T-type solution. This allows a reduced volt second to be applied on the inductor, assuming the same operating frequency. And this again allows for smaller magnetics. A higher efficiency can be achieved with the same switching frequency. And a lower voltage distortion can be achieved because now there are three levels of switching in the power converter. The disadvantages, of course, continue to stay that you would need 1200 volt devices, which are carrying a lot of volts and amps, and increased bus capacitance, and then uneven loss distribution because you have 600 volt devices and 1200 devices all used in the same power converter. Having said that, let's go look at these power topologies which enable the use of 650 volt devices, which we termed as the multi-level power converters. So shown here is ANPC 3-level power converter. In this case, you see the use of certainly more switches. So the semiconductor spend is going to be higher, but can be more than compensated by reduction in the size of these magnetics, because now you have a situation where a lower volt second is applied on the inductor, and inductor effectively sees twice the equivalent frequency at 50% of the bus voltage, which really enables the use of smaller magnetics and also simplified isolation between the windings of the inductors. The FETs themselves now see only half of the bus voltage each, which allows the use of the 650 volt switches, which have better switching performance, as we have seen earlier. And that really gives you the opportunity now to switch these devices at a higher frequency, further reduce the volt cycle balance, and in the end, achieve a smaller piece of magnetic to be used in the power converter. A fourth example here is a flying capacitor 4-level converter, which needs the same number of switches, but in this case, the switches see, the inductor sees 3 times the equivalent frequency at 1/3 the bus voltage, so it allows the smallest size of these inductors. Each FET sees only 1/3 of the bus voltage, and since there are multiple FETs here seeing the same voltage, there's more even loss distribution and much lower distortion of the voltage output. And certainly because there are more switches, the conduction losses are higher, and there's increased control complexity for controlling this converter. But then again, the opportunity here is if you're able to run all of this at higher switching frequencies, then you have the opportunity to reduce the size of the magnetics and enjoy the associated benefits with that. Next, we'll show you some examples of these multi-level converters, which have been successfully implemented with these 650 volt switches. This is an example of a bidirectional 3-level converter processing 800 volts on its output, and with a 3-phase AC input and 6.6 kilowatts of power. This again uses 650 volt GaN FETs operating at 100 kilohertz of switching frequency and reaches a high efficiency of over 98% at full load. With the low component stress, you get lower switching losses and improved system reliability. And there are smart ways to control so that fewer PWM modules are needed to control the increased number of switches in the system. A quick look comparing the efficiency between GaN and silicon carbide here shows that GaN is able to achieve over 98.5% efficiency with very clean, low distortion voltage waveforms, and able to get this high efficiency all the way down to about 1.5 kilowatts and over 90% efficiency at light load. GaN, because of its better switching capabilities at the same frequency, offers over 0.5% improvement in efficiency at full load and between 2 to 3% at light loads. Here is an example of a 4-level flying capacitor power converter, which is processing 5 kilowatts of power between a 900 volt bus and a 3-phase AC input. Here you can see the comparison between different technologies, including silicon IGBTs, typically operating very low switching frequencies. And with gallium nitride, we are able to get the frequencies much higher than both IGBT and silicon carbide, resulting in higher power densities, over 3 times our power density, and still higher efficiency compared to the other devices operating at lower frequencies. And all of this can be implemented without a cooling fan. So it's a convention cool arrangement, which again comes from the fact that with the lower switching losses, these GaN devices are able to deliver overall higher efficiency for the entire system. Again, achieving over 99% peak efficiency with a harmonic distortion less than 3% for the 3-phase AC outputs. The integrated gate driver for the GaN FET, showing the switching waveforms during turn-off, very clean switching waveforms with very little overshoot, and having a DVDT as high as 100 volts per nanosecond, which really contributes to reducing the overlap losses in these hard switching applications. And of course, the low inductance package mitigates the voltage spikes seen during these fast switching transients. A relative comparison of the different cost and size of the components used in this 4-level converter. You can see here in the traditional half-bridge arrangements, the size of the whole system is dominated by the size of the inductor, which is again directly resultant to the fact that these are operating at lower switching frequencies. But as we're able to increase the switching frequency and in fact the equivalent switching frequency seen by the inductor, it gives the opportunity to reduce the size of the inductors dramatically and achieve a lower overall volume for the inverter. From a cost perspective, there's no doubt the semiconductor spend is increasing, but again, this reduction in the size of the magnetics can more than compensate for it, achieving lower overall relative cost for the multi-level converter approaches as opposed to the traditional half-bridge approaches. Now let's look at the stacked half-bridge arrangements. We spoke about multi-level converters, but there's another commonly used arrangement which is called the stacked series half-bridge. This shows the example of a DC to DC converter, which is running off of a high DC bus over 900 volts DC. On the primary side, you have 650 volt devices arranged as a stack of 2 half-bridges in series on the primary side, and then you have half-bridges on the secondary side, which are operating between 2 split capacitors. The way the transformers are driven is between the switching nodes of the 2 half-bridges on each stack, which is then unfolded and rectified on the secondary side. And in order to manage high battery voltages, the output capacitance is again connected in series, which really results in a very elegant architecture that is able to support not only higher DC bus voltage on the primary side, which would be typically the output of a 3-phase PFC, but also enables a high DC bus voltage in terms of a high voltage battery on the secondary side. What's also nice about this architecture is by simply manipulating the output connections from being the series connection shown here to a parallel connection, it is even possible to support lower battery voltages with minimal change in the rest of the design. And putting this in context of a real application, such as 11 kilowatt onboard charger used in electric vehicle applications, and comparing the contemporary architectures of 1200 volt silicon carbide devices versus 650 volt GaN devices, it becomes very quickly obvious that even with silicon carbide solutions, owing to the need to operate at frequencies with the higher DC bus voltages, parallel modules are often used, that each module is processing half the power, and then the whole power converter is delivering the total 11 kilowatts. That results in the use of 2 transformers and 16 power switches, which is exactly the same number of transformers and switches used with the 650 volt GaN solutions. This really goes to show that in a practical implementation, in the end, the overall number of switches is not necessarily going to be higher in a multi-level arrangement such as that is shown here. For sure, the RDS-on of these GaN switches have to be optimized because of the higher current owing to the fact that they're now switching with half the bus voltage. But that is more than made up for, again, in terms of the fact that there is opportunity to reduce the system cost by using smaller transformers. And in this case study we have done here, you can see the transformers that can be used can even be a planar transformer, which is 65 cc in size, for delivering 11 kilowatts at a resonant frequency as high as 750 kilohertz. This again helps to reduce the cost of one of the most expensive components in the system, and overall trade-off between the money spent on the semiconductor versus the magnetics, while still achieving a much higher power density in the overall system. Okay. The similar stacked half-bridge concept can also be extended in a traditional AC-DC onboard charger or AC-DC power supply, where if you have a need for a higher voltage on the output, we can simply change from half-bridges arranged as shown here into like a stacked arrangement with a split DC bus capacitor. And this, again, allows the capability for using 650-volt devices, which can now match the switching frequency of the same 650-volt devices, which are going to be used on the primary side with a 400-volt DC bus that results from a single-phase AC connection. As opposed to other applications where if you were to use a 1200-volt devices in the traditional configuration, you would going to be limited in the overall switching frequency of the converter by the limitation in the switching frequency of the 1200-volt devices, resulting from their higher switching energy loss. So really, there's a benefit to using 650-volt devices all throughout in order to be able to achieve a higher operating frequency for the power converter. Here is another variant of the stacked half-bridge arrangement, where you can see a more symmetrical structure with a split DC capacitor on the primary side as well as on the secondary side. And this enables the use of a more traditional full bridge structure on the primary and the secondary with the transformer connected in between. And this basically simplifies the overall arrangement, but there is of course the additional task of achieving simultaneous balancing of the voltage of the capacitors on the secondary side as well as on the primary side. So this really brings me to the final conclusion of this presentation. And just to reinforce some of the key points we've made, first off, the superior switching performance of the 650-volt GaN FETs provides an exciting opportunity to be able to increase the switching frequency of the power converter. This is a very compelling alternative against the conventional approach to use the traditional two-level converter with higher voltage rated switches. Particularly, the lower switching energy figure of merit of the gallium nitride device brings merits both for hard switching and soft switching type applications. The multi-level converters I showed earlier were all examples of hard switching, while the stacked half-bridge examples I showed were more resonant topologies, hence operating in soft switching. So for both of these kinds of power converters, 650-volt GaN devices provide a compelling advantage in terms of being able to achieve higher switching frequency. The second key point, a simple and clever manipulation of the power topology and the architecture easily enables the use of these 650-volt switches, even in those applications where the DC link voltage is much higher than the voltage capability of the device. There is absolutely no need to be intimidated about these power topologies. These are pretty well understood, and so are the control algorithms related to it. There is very quickly a mature ecosystem developing of the DSP control solutions, the isolation products, the sensors, and the FETs. All of that is needed packaged into reference designs, which can make for a more simplified and smoother development experience with these multi-level converters and the stacked half-bridge arrangements. So with that presentation, I hope I've made a case here for why you should certainly look at 650-volt devices, especially gallium nitride devices with an integrated gate driver, in order to be able to increase the switching frequency of your power converter by twice, thrice, and to, in the end, result in achieving smaller size of magnetics and higher power density for your application. Thank you very much for your time, and we'll take some questions. Okay, I see a lot of questions have been going through our moderator here. There's a question about why GaN switching loss is worse at lighter loads compared to silicon carbide. This, in the end, comes back to the output capacitance inside the devices. For the ones we've compared and the state of the technology, it starts off with lower higher switching losses due to the output capacitances, but once the overlap losses come into picture, which it will, even with very small currents, we immediately start seeing gallium nitride devices starting to have much better switching energy performance. There's a question about what would be the loss comparison if you use 650-volt silicon carbide devices in the same topology. As you can see, yes, we have compared the 650-volt silicon carbide devices with 650-volt GaN, and you can certainly see that GaN has much lower switching energy performance. There's a question about whether the slides will be available. Certainly, for those who have registered for this presentation, the slides will be made available by the end of this week. Okay, with that, we will conclude our presentation, and thank you very much for your time and interest today. Please visit www.ti.com/GaN to learn more about these compelling devices for high-frequency power converters. Thank you.